Hello and welcome back, guys. This is Mr. Zoyas greeting you, the real Mr. Zoyas, I might add, none of those imaginary Mr. Zoyases. And we are back for another episode of SIP Zoyas. That's right, I finally decided on a name, SIP Zoyas. It's weird, sounds awkward, but I'm pretty sure that's how most things get their beginnings, right? Like, isn't it like all good things have an awkward beginning? I think Einstein said that. I don't know. Let's go ahead and start. We're going to be talking about factoring in general, and we're going to be building upon these factoring skills, and we're going to do more than just factoring by grouping, right? That's kind of our bread and butter that we learned before, but now we're going to go back, and we're actually going to kind of touch on some roots of it, and then go further with these roots, and also learn about a few special cases. So, let's stop talking about it, and let's just get into it. Factoring continued. So, again, going back to our fundamentals, factoring is the process of finding a common multiple and removing it such that the remaining expression is shown in terms of multiplication. Right? So this could be something as simple as just realizing, 6 is 2 times 3, so I'm just going to write 2 times 3 instead of writing 6. Right? That's all that factoring is just finding a common multiple, sometimes with multiple terms, as we see going forward, and removing that from the expression. A factored expression should be able to be multiplied back into its original expression, right? And so this is really a fundamental idea of math, that whenever we do something, there should be some kind of reversibility of it, right? And that's an indicator of good logic. That's an indicator of consistency. If we can go forwards and backwards with it, that's a good sign. We like that. So, realize real quick in that this is a way to check your work, right? So you factor it, then see if you can go back, right? See if you can multiply it back in to get back what you originally started with. Okay, so baby stuff, right? Fundamentals. Find the greatest common factor. Okay, so we're examining the number 90 and 300. Okay, so we want to rack our brain. We want to find out what whole numbers can be evenly divided into this. Right? Well, I know that 10 can be evenly divided into 90, and 10 can also be evenly divided into 300. So I can write 10 times 9, comma, 10 times 30. Okay, and that's realizing that we have a common factor of 10 in there. Okay, because 10 times 9 is equal to 90, right? We just reversed it, that's good. And then 10 times 30 is equal to 300. We just reversed it, and that's good too. And so cool, we found some of the common factors, but spoiler alert, there's more in there. And you guys probably already know this because we're at a higher level. But that remaining term, go ahead, we can play Dora the Explorer if you really want to. Go ahead and shout it out if you see it. That remaining factor in there is 3. Okay, 3 can be evenly divided into both 9 and 30. So we could then also factor out a 3. And so multiplying that with the 10, we would have 30 times 3, comma, and then multiplying that with the 10, we would have 30 times 10. Right, this one actually just kind of switched places, and it almost seems redundant in a way, but the important thing to take out of this is that both of them have a 30 which can be multiplied into them. If we wanted to, we could divide both by 30, and we would still get integer values as our output. Okay, so now let's go ahead and factor the expression. So this is where we're going to want to look for a common factor, and then factor it out, similar as we did to this. Okay, so you're going to want to look at both terms and ask yourself, what is a shared factor? What is a shared multiple? Right, well, we see 2 times x to the third power minus 6 times x. Right, check that out. They both have x's that are being multiplied in there, so I'm going to go ahead and remove one of those. Okay, so that'll leave me with 2 times x to the second power. Remember that exponent means repeated multiplication. We took out an x, so that exponent's going to go down by 1. Minus, and we only had one x multiplying there. Oh, God, that's a terrible minus. So we're going to be left with just 6, because that's all that's left over. God dang it, now it looks like an equal sign. I can never win. This is why you never do math in pen. Okay. And so let's go on and keep looking, because there's still more in there. And it's actually, this is a very common thing. It's easy to miss one of the factors in there. So you the more you practice this, the less you're going to miss something. That's just how it goes, right? This is kind of a little bit magical. It's a little bit of a art the way this happens. It's a kind of summation of all your math abilities. So if you have a lot of strong math abilities, this is really easy. But if some of your fundamentals are weak, this is going to be a little bit harder. But again, just because it's hard doesn't mean we don't do it. And oftentimes because it's hard means we should do it, because it's building the things that we need to work on. So the remaining factor in here, I have a 2 times x squared minus 6. Well, there's a factor of 2 in both of these because we can divide 6 by 2 and get 3, right? So 2 times 3 can equal 6. So I'll also pull out a 2 and have 2x times x squared minus 3, right? And that's left behind. That's kind of, we can think about it, if I took this term right here and divided my original term with it, I get what's left in here. Okay? And going backwards with it, right? Checking this, what we can do is we can distribute this back in, right? So 2x times x squared. I'm going to write proof down here. So 2x times x squared would be 2x cubed, and 2x times negative 3 would be negative 6x. Boom. Right back to where we started. We love it. We love it, right? In math, we love getting nowhere. That's the best kind of journey. Right? A little spoiler alert. It's about the journey, it's not the destination. You end up in the same place every time. Okay, so again, what's the common factor? Now this one's a little bit hidden. It might be easy to skip over this. You might just see x plus 3 to the power of 2 and x plus 3. Well, I guess it's that. So the hidden step that I'm talking about is we condensed this multiplication into an exponent. So remember, we can write this exponent like this. Okay? And in doing so, it can become even more obvious that we have a factor of x plus 3 in here, but on top of it, we can now pull one out, and we're going to see how if we divide by an x plus 3 for both of these, that'll take out one of these and one of these, leaving behind just this and this, making it more obvious that we'll have one of these left behind. Okay, so we can factor this out. So factor out the x plus 3 to right here. And then what is left behind? We have x plus 3 left behind. And I'll even put parentheses around that. And then we took out that x plus 3, so what's left behind are minus 4. Okay, and a really good way to think about this is, if you have your factors explicitly written, you can just cover them up and then write what's left behind, right? So for this one, we would cover up one of our x plus 3s, and we would have x plus 3 left behind, so we could write that right there. And then covering up our x plus 3, we would have minus 4 left behind, so we would write that right there. Okay? And there's actually one extra step we can do with this, right? So we do have parentheses right here, but realize if nothing's multiplying or dividing those parentheses, we can just drop them at will. So we can actually rewrite this, just bringing this term back down, we don't touch it. X plus 3, if we drop those parentheses, we then have some like terms that we can add, 3 minus 4. So we can write this as x minus 1. Cool, right? Okay, next one. So this one may not be as obvious, right? The factor may not be just jumping out at us, but what we want to do with things like this, sometimes we'll see a fraction in our term, and we may want to remove that out of there. A lot of times we like our factors to have whole numbers in front of them. So we can go ahead and try and just remove this fraction. So we're looking to factor out a 1/2, right? So this would be dividing both of these by 1/2. So if we did that, it would just get rid of the 1/2 over here, right? The 1/2 would come out. 1/2 x divided by 1/2 would just leave us with x. And now what's 4 divided by 1/2? Right? You may know that's 8, which is awesome. But now we can even go ahead and think about this a little more qualitatively, right? If we were to multiply a 1/2 back into here, what would this have to be to go back to a 4? Okay, right? So if we're pulling out a 1/2, that means we're going to need to multiply this by 2 to counteract that 1/2 when it goes back in. Right, so the 2 multiplied by the 4 is going to bring us to 8, so when that 1/2 does get distributed back in, it's going to absorb it, I guess, in a sense, right? You can think of it like, you know, canceling each other out. And you're then going to have, right, distributing this back, and you'll have 1/2 x plus 4. Okay, gets us right back to where we started, which is good. It's a good sign. Consistency. We want consistency in all of our relationships, even math ones. Okay, so now we're going to have some special cases of this. So our special cases are going to be there are 2 square expressions that are special cases. One is perfect squares, and the other is a difference of perfect squares. Okay, and so let's go ahead and see what these look like. The equations look like this. So a squared plus a times 2 times a times b plus b squared, and that's going to equal quantity a plus b squared, and a squared minus b squared equals quantity a plus b times quantity a minus b. Okay, these are our 2, and right, respectively just means in order, so our perfect squares are the first one. Okay, I'll go ahead and circle our perfect squares. And then our difference of perfect squares is going to be right here. Okay, and that's boxed in. But let's go ahead and think about that, right? So this is a perfect square because we see that it's just a plus b squared. Right? It's a perfect square. We just took a term and we squared it, and this is what we got out. Right? We actually took a binomial and we squared it. Right? We have 2 terms, we squared that binomial, and this is what we get out. And over here, a difference of perfect squares. Well, let's think about that. We have a squared minus b squared. Right? That difference is the minus, so we have a perfect square minus another perfect square, so it's a difference of perfect squares. Right? This is actually a great name. It kind of makes sense. And so, as we see, when we have things that look like this, they can turn into this. Right? We can then factor this into this, and if you don't believe me, go ahead and do your box method. Not FOIL method, because I care about you guys and I don't want you to get hurt. But do your box method and see that this is a true statement. And to be honest, I kind of like to think of it the other way around. I like to think of having this, doing our multiplication, doing our polynomial multiplication, and seeing how this comes out. Okay, and I'll actually, I'll go ahead and take a quick second to show how these 2 things equal. It's really great to see this. If you don't want it, of course, skip over it. But it's going to look like this, right? If we have a plus b, quantity squared, well, we can use our clearly superior box method and just write a plus b over here and a plus b. Okay, going through the multiplication, we have a squared times a times b times a times b, and then b squared, which is then going to give us out an a squared term plus, now check this out, we have a times b, right? And I'm just going to go ahead and write it out, a times b, and then plus another a times b, and plus b squared, right? And we have some common terms in there, right? We have some like terms, our a times b. So it's going to be a squared plus 2ab plus b squared. Okay, and check that out, that's our rule, right? We can easily get that out just by doing the multiplication of a plus b squared. And we're going to see it gets us there. Now, so I guess let's take a second to kind of understand what's happening, right? We have the same term being multiplied by itself, so that's going to give us a square on the ends of it, which makes sense. But now when our terms get multiplied by each other, right, the a times the b and the other a times the b, that's the same multiplication, right? So if it's the same multiplication, we're just going to have 2 of that, or twice that, right? That's why we have a 2ab. And this makes a lot of sense, right? Like it's our first term squared, last term squared, and then twice our first term times our last term. Okay, and this is, realize we call this a special case because it's a pattern which shows up, and it's a pattern which is easy to notice, and there's a equation that we can apply to this which can make the factoring process go a little bit quicker. Okay, understand that when we do this, if we see something in this format, we don't have to go through and do our entire magic method. We can just go ahead and apply our knowledge of perfect squares. Okay, and likewise, I'm going to go ahead and explain the difference of perfect squares. So now we're going to look at, right, we have this situation, and it's very easy to inquire, what if I had a minus b times a plus b? Right? What if I had this same situation except one of my binomials had a minus term in there, right? What would happen then? And this is what happens. It's very interesting. Again, it produces another pattern, and it's very easy to kind of reason why this is happening. Okay, so putting this term up here, and then taking this term, putting it down here, we're going to have a and negative b right there. So we multiply these, so a times a is a squared, a times b is ab, a times negative b, right? We have a negative, right? And let's go ahead and just reflect on what just happened, right? We had a times b, and then we had negative a times b, right? When this happens, realize we did the same multiplication, except one of them had a negative. Right, so we have same multiplication of a positive, and then same multiplication of a negative. Right? We do one thing that's the same, or we do one thing that's a positive, and then we do that exact same thing that's a negative. What do we expect to come out of that? Right? We do a positive version and a negative version of something. Right? We would expect those things to cancel out, and indeed, that's what they go ahead and do. So, doing this last multiplication, b times negative b is negative b squared. Right? And then we write this out, and we see we have a squared plus a times b minus a times b minus b squared. And lo and behold, like we predicted, right? We did the same multiplication except one was opposite, and now we have two terms that can cancel and reduce to 0, giving us a squared minus b squared as our remaining expression. Okay? And so again, this is a noticing. This is a noticing that when we have two numbers multiplied by each other, two binomials multiplied by each other, and one is a positive version of it, and one is a kind of negative. One has a difference, one has a sum. Then this happens, right? And then what is this? This is, we have two binomials, both of which are a sum of the binomials, being multiplied together, and then this is what comes out of it. Okay? The difference of perfect squares, the perfect square. Okay? And I guess we could, it might be better to call this the sum of perfect squares. Right? But I guess that would have different implications to it, but realize that there's the plus sign in here that's making this work, and the minus sign in here that's making this work. Okay, so let's go ahead, and I'm going to take advantage of this pattern that I just noticed. Right? I'm going to take advantage of this pattern in these problems, so I'm not going to be doing magic method. But it's incredibly important to note, and I know that this is kind of a long tangent, but realize magic method still works. That method that we got, the magic method, nothing's wrong with it. It still works. This is just kind of a pattern that we notice that we can apply to save ourselves some time. Right? This is like that mature level of math understanding. This is to the point where you've done the basics so much where you have those fundamentals, right? You have that magic method. It's going to work no matter what, right? It's your go-to method. It's always going to work. Solve any kind of factoring problem you throw at it. And now this is kind of a consequence of certain situations that are in it. Okay, I can't emphasize that enough, right? If you can't master this, if it's a little difficult to remember these two equations, these two patterns, don't worry about it, right? These are variants. Focus on the non-variant, focus on the main aspect, right? Focus on the magic method, and then master the variance, right? The core comes first, that magic method core comes first, and the variants come afterwards. Okay? So, taking advantage of these equations, right? Taking advantage of my variance, I'm going to look at this and I'm going to realize, well, I have a 4 there, which is a perfect square. I have a t squared, which is also a perfect squared. It's maybe a little unfamiliar for us to say that, but it's a t times a t, right? Just like 4 is a 2 times a 2, which makes it a perfect square. That's a t times a t, which is a perfect square. Plus 4t plus 1 is 1 a perfect square. Well, indeed, right? 1 times 1. And this is going to be your key indicator. You're going to see perfect squares on the end, and that's when you want to question this term in here, right? Is this middle term 2 times the square root of your outside terms? Meaning that, right, whatever the base of this is, so we could think of this as like 2 squared times t squared plus 4t plus 1 squared. So is this 2 times t times 1 doubled, right? Is this 2t times 1 doubled, right? 2 times ab. And indeed it is, right? So 2t times 1 is 2t, doubled is 4t, right? So this is going to be a perfect square, and I can go ahead and use this equation on it. So I'm going to see that this is just going to equal t plus 1. Okay? And that's just following my equation that's I identified, and actually this would be great practice if you're using this variant, which I want you to do. You know, I want you to do this if you're going to use the variant, is say what your a and b are. Right here, my a is 2 times t. Here, my b is 1. Okay? Hence, it's just going to be a plus b squared. Okay? Now, truly, you know, I truly challenge you. I'm not gonna, well, you know what the heck, it's a video, right? You can fast forward past the parts you don't want. I'm gonna go ahead and do magic method over here to show you how magic method can also work, right? Magic method isn't bad. This is just a shortcut. This is a smart cut. So let's go ahead and look at that magic method. Okay? So we got the M, the A, the G, the IC. Right, we are going to be pros at this by the time we're done practicing. So we're going to multiply, and I'm going to go ahead and just kind of set this problem up over here so we don't get confused. ax squared plus bx plus c, that is my standard form, and my equation is 4t squared plus 4t plus 1. Okay? Now multiplying a times c. A times c is going to equal, well, my a is 4, and my c is 1. So I have 4 right there. Okay, so now I want to add to my b term. What is my b term? My b term is just 4. Right? So the question here is, what are the factors of 4 that add to b? Right? What are the factors of 4 that add to 4? Well, notice how 4 is a perfect square, right? So that would just be 2 and 2. Right? Hence, it's a perfect square, right? It comes full circle. It's all in the name. It's a perfect square. Okay, so we could then group our terms by that. We could have 4t squared plus 2t plus 2t plus 1. We're going to group these appropriately, right? Our first two terms, our last two terms, and then factor out what we can. So we're going to have a 2t that we can pull out of this first term, leaving us behind with a t plus 1. Sorry, 2t plus 1. My bad. right? So we divided t times 2 into here, and that gave us a 2t plus 1. And then plus, what can we factor out of here? We actually can't factor anything out of here. 2t plus 1. And so then we pull out our common factors, which now happen to be this and this. So we have 2t plus 1 factored out, and left over a 2t plus 1. Right, and that's equal to what's over here. That's equal to just 2t plus 1. Okay, magic method still works. This is just quicker. And if you train yourself, if you do enough of these and you notice, when do I have a perfect square, then you can go ahead and just apply that formula to seamlessly get through it. You can increase that speed on the ACT exam, right? Increase that speed, increase your results. Okay, now let's go ahead and look. And so, this is going to be, right, spoiler alert, this is a difference of perfect squares, right? You guys already knew that was coming. But how could we identify this? And we're going to identify it similar to the way we identified perfect squares. Right, we're going to look at the highest degree term and the lowest degree term. And if we notice squares in there, that should tip us off, right? It's going to be one of these two. It's going to be a perfect square or a difference of perfect squares. Right, so then what takes us all the way? We see that minus sign. The minus indicates the difference. Okay? And so, knowing that this is our difference of perfect squares format, right? A minus b times a plus b is equal to a squared minus b squared. I notice that format matches perfectly. 16 is a perfect square, y squared is a perfect square, and so is 9. So I'm going to go ahead and express just a little bit more clearly. I'm going to write 4 squared times y squared minus 9. Or sorry, minus 3 squared. And now maybe you don't need to do this, right? Maybe you can just realize what the base of those perfect squares are, and then just say that's what a and b equal. But if you don't, that's okay. Go ahead and take that extra step to secure your logic. Okay, and then we could say that's 4y squared minus 3 squared. Okay, in which case we can see this matching perfectly with our difference of perfect squares format. Okay, so we're going to see that here our a is equal to 4y and our b is equal to 3. Right? Not negative 3 because the negative is accounted for in there. That negative is already there, so we don't want it. We just want this number, right? And this is really just, this is, I think, great visual logic. You look at it and you see how the two compare, and then you go ahead and write it like that. Right? The only thing missing, right? The negatives are already in front of there. The negative's right there. The square's right there. Square's right there. So what must be b? Just a 3. So then we can write this in this format now using our a and b. So a is 4y minus b, which is 3, and then a, which is 4y, plus b. Whoops. God dang it. Not b. I'm sorry. Plus 3. Oof, man, good thing I'm catching these. Otherwise, I would be doling out Z-Bucks for days. Okay, and then this would be our final answer. Right there. Okay, just like that. And again, magic method would work for this too. There's no reason why it wouldn't. And I'm going to challenge you to go ahead and do magic method, but I'm not going to do it in here. That's your challenge. Okay? Understand it would work the same way I did it over here and it worked. It's still going to work over here. Okay? Magic method is our bread and butter. These are our variants. Okay. So, very last part, the home stretch, the factor by grouping for higher degree polynomials. And now don't forget, our factor by grouping is really, when we do magic method, that's just factor by grouping. Right? We have the magic method to help us remember what to do. But now understand that magic method is needed when we have things of square terms or lower. Right? specifically when we have trinomials, right? Looking back here, a trinomial, 1, 2, 3 terms, then magic method's really helpful. It's helpful for breaking up that middle term so we can then have a 4-term expression which can be grouped and factored appropriately, right? But now we're going to look at higher degree polynomials, which they're already going to have 4 terms in them. They're already going to have 4 things in here, so we don't have to go through that breaking up part. We don't have to decompose any of this. We can just kind of skip that, start grouping them, right? Look for terms that have the greatest common factor, and then group them, okay? So they can be factored just the same way as degree 2 polynomials, except we're just going to start grouping them, and then look for that greatest common factor. And then, of course, factor it out, right? We find the greatest common factor, we don't just look at it and say hi, we factor that bad boy out. So, looking at this, what are some things that I can group together? What are some common factors? Well, I have x to the power 3 and I have x squared, right? Those both have factors of x. So I'm going to go ahead and draw my group around them. And I have 2x minus 2. Well, that factor is just screaming at us, right? We have a factor of 2 in there. So we can go ahead and factor out from both of these. So factoring out from our first term, we have x squared, right? We have x to the third power, x to the second power. We can factor out 2 of those. Okay, so x and minus 1 are left behind, right? If we divided both of these by x squared, we would see this is what we get left behind. Okay, plus, now let's go ahead and factor out over here. So we have a 2 that we can factor out. So we have an x left behind and a minus 1 left behind. Well, how do you do? Look at that. What do we have as a common factor? Right, what's our common factor here? It's x minus 1. So we're going to go ahead and pull those guys out. Same way we do with magic method. Notice we just didn't have to do the a times c adding to b stuff. Right? We just need to group them. And then we can go ahead and pull that out. So we pull out our x minus 1. And what is left remaining? Well, we have an x squared right there. And a plus 2 over there. Those are the 2 things remaining. X squared plus 2. Just like that. Okay? And that's our factor. That's what this is what we get out of this, right? This is what it factors into. Okay? Now again, remember, this is reversible. This reversibility means you can check your work. You should be able to multiply these binomials to get back to here, your quadnomial. I actually don't know if that's the right way to refer to it, but quad meaning 4, nomial meaning terms. We have 4 terms up there. Okay, and I'm actually not going to go and do it, but I'm going to set you up to check this. Right, so how we could check this is with our box method, right? With our box method, I'm just going to go ahead and say box method's the only method. There's actually, right, because if we're talking about legitimate methods over here, we know FOIL isn't legitimate. We know that it's like the peasant's method. Right, this is like the king's method. The FOIL is like the peasant's method. So we're going to go ahead and do our clearly superior king's method, the box method, and have x to the power of 3. And then I lied. I said we weren't going to do it, but you know what? That's what happens with math. You just get lost in it. It's so much fun. Before you know it, you're just doing problems, and you're like, wow, I've spent 30 minutes of my life doing this, and I don't entirely regret it. At least I don't. Hopefully you don't either. Okay, so we'll have left over an x to the power of 3 minus x to the power of 2 plus 2x minus 2. Lo and behold, it matches. It matches, we did it right. Cha-ching. Next one. Okay, again, this is the same idea. You know, we just don't have to break up that middle term. We can just group them and then start factoring. So, I'm going to look for things with a common factor in them. Now, there's a few ways you could do this. If you want, you could notice that, oh, actually, sorry, I lied. I thought I saw something, but I didn't. Okay, so the way to group this, right, you see an x to the power of 3 here, and an x squared here, right? These both have a factor of x in them. So let's go ahead and group those, and write more specifically a factor of x squared in them. And then minus 6x plus 3, what do these both have a factor of? Well, of course, it's 3. So we're going to go ahead and group this, but remember we want to keep that minus with the 6, right? That's a negative 6. So we're going to keep that there, but then put a plus sign just so we don't forget that these are all being combined, right? They're not being multiplied like this might suggest otherwise. Okay, so now let's start factoring, right? We have 2x to the power of 3 minus x squared. What's our common factor? We have a x squared common factor, leaving behind a 2x minus 1. And then over here, what's our common factor, right? We have negative 6x plus 3. What's our common factor? It is negative 3. Okay, and so let's go ahead and check out. So, right, why did I say negative 3? So this is kind of where we want to be a little bit more clever. And, oops, forgot to write that plus sign. This is where we want to be clever, and we don't want to have a negative on this term, right? For the most part, we don't like our first term in our binomial or any of our terms to have a negative on it. Okay, and we're going to see that when we do this, it actually creates the perfect situation with these remaining terms. So negative 6x divided by negative 3, right? That's going to leave us with a 2x. And then negative 3 divided by negative 3, that leaves us with a negative 1. Right, notice how when we take out the negative in there, it sets these up so they perfectly match, which can then be factored, right? If we didn't do that, they wouldn't quite match. They'd almost be there, right? They'd almost be there. This would be a plus sign, that would be a minus sign. And that's okay, but just realize in that, you can then factor out a negative to take it all the way, and to then have them match. Okay? So we're going to go ahead and factor both of these out. So we have 2x minus 1, which can be factored out. Those are our common factors. And then we have an x squared minus 3 left over. Right? Because remember, you just cover up what we factored out, and that's what we're left with. X squared minus 3. Just like that. That's a little multiplication dot, just to make it explicit. And again, if we want, we can go back and check our work by boxing it out and seeing that this equals it. Side note, of course, disclaimer before I get scrutinized or burned at the stake, possibly from people outside of our class, FOIL method is perfectly acceptable. I just like to hate on it. It's just kind of a running joke in our class. So with that said, yeah, factoring, right? Expanding it. Factoring is an excellent skill.